Hello, Physics 135 students, and welcome back for our 15th virtual class. This will actually be our second to last one of the semester. And first, we have another icebreaker, simply light side or dark side. Go ahead and pause the video and answer that icebreaker now, no additional context. Okay, unpause. So just kind of, a fun gut instinct, whatever you prefer. I personally prefer the light side. Although maybe I have some dark side tendencies. So this is, not necessarily a Star Wars reference or anything. I think of it as being a little bit more Star Wars-y. And definitely as far as the Star Wars universe goes, I would say I prefer the light side. Now, in terms of our universe, rather than the Star Wars universe, it turns out that if you prefer the dark side, you would be in the majority. And we've talked about dark energy previously in this class. Today, we're going to talk about dark matter as well as a few other things. First, very, very important today, exam number 3 is due, and your semester-long research project will be fully and finally due and done next Sunday. So that's very important for both of these, really. I guess technically, exam number 3 is only 5 points, whereas this final paper submission is, I believe, worth 8 points, but both are very, very important. Those are percentage points towards your final grade. And regarding today, we're going to talk about the evidence for dark matter and how this relates to cosmology as a whole through this kind of jargon, but I think it really makes sense. The phrase is large scale structure. And then we're going to build off of what we were covering not last week, but 2 weeks ago with respect to the discovery of the cosmic microwave background by Penzias and Wilson, which was later confirmed by Kobe. In particular, we're going to talk about the temperature variations that were found in the CMB, which relate to this previous bullet point, in fact, and then how that has changed to some extent from WMAP to Planck, and then discuss the power spectrum. And then next class, which will be our last class, it will really not be that much of a lecture. There will be a very, very short lecture, and then I have quite a few more open-ended activities for y'all to explore, since it will be the end of the semester. And for today, admittedly, it's also going to be a somewhat shorter lecture, in particular because I want you all to have an opportunity, ideally, to enjoy the one of the more open-ended worksheets, exploring some really fun animations for the cosmic microwave backgrounds power spectrum, and how that informs us about dark matter, as well as dark energy and a lot of other properties. So, talk a little bit more about that towards the end of this lecture. And we have a couple of other worksheets today. So first, on dark matter, we have our first three attention checks. One, what is the evidence for dark matter? Two, what is dark matter made of, or at least what are the candidates for what dark matter is made of? And then three, is the relationship between dark matter and the formation of large-scale structure in the universe. So as a result, you'll learn what large-scale structure means a little bit more rigorously. And in terms of dark matter, this really is the universe's biggest mystery. We have no idea what exactly dark matter is, although we think that dark matter nevertheless plays a crucial role in our universe. And what is being shown here is a cosmological simulation that starts with the ingredients from the first 3 minutes, just mostly hydrogen, a little bit of helium, but then overwhelmingly dark matter, and forms the structures in the universe that match very well with observations today, the so-called superclusters or galaxy clusters, where there are many, many galaxies together. Every single dot here, by the way, is a galaxy, if not a galaxy cluster. And then these form at so-called nodes of the dark matter cosmic web. And then there are also significant filamentary patterns where eventually the nodes connecting which are connected by these filaments, might merge. And then there are so-called cosmic voids, the kind of gray regions or light gray regions where there is a pyasti or they're relatively devoid of galaxies. So again, really, I think interesting subject matter for me. I hope that you all enjoy this unit. And as you all have learned about at this point from reading the book, hopefully uh, uh, a lot of you, it seemed like, have fallen off submitting the reading assignments, uh, which is not the most ideal thing. The completing the book is a major part of this course in terms of the learning the material. It goes a lot deeper than we're able to go during these lectures. Now, in terms of the first evidence for dark matter, it dates back 90 years now, getting towards 100 years. In 1933, a Swiss astrophysicist named Fritz Zwicky, who is not a very nice person. You can see that he has a big frown on his face. But anyway, he was still a very good scientist, nevertheless, and found that in galaxy clusters, it seemed like 90% of the mass was invisible. And he was largely ignored regarding this result. There are a few good reasons for that, admittedly. It turns out now that we know that the X ray emitting phase dominates the visible phase in galaxy clusters also by a factor of 10. So that was one, missing piece in the 1930s. Perhaps the reason why Fritz Zwicky was more of ignored because none of his fellow astrophysicists were saying, well, you forgot the X-rays. None of them thought that the X-rays were significant at that time. Maybe Fritz Zwicky was ignored because he referred to people who he didn't like as so-called spherical bastards, as some of you have commented in your reading assignments, um, because in his own words, they were bastards no matter which way you looked at them. So a kind of clever insult, admittedly, although not a very nice thing to refer to people by. It was a couple decades later before a fellow iconoclast who was not nearly as reviled, thankfully, although nevertheless, fortunately experienced gender discrimination at Princeton and to some extent at Harvard as well. So this is Vera Rubin. We now have the Vera C. Rubin Observatory named in her honor. And whereas Fritz Zwicky, I guess I maybe glossed over it a little bit, was looking at the motion of galaxies in galaxy clusters and suggested that there must be a lot of mass that was invisible, Vera Rubin did something similar, but was considering the rotation curves of spiral galaxies and found faster rotation than you'd expect from the matter that was directly observable. And so this suggested that there's some additional missing mass. In terms of how to understand this, let's look at a rotation curve a little bit closer to home. This is the rotation curve of planets in our solar system. And you can see that Mercury has the fastest, uh, really, we would say revolution speed or orbital speed. So Mercury orbits the sun most rapidly, Venus orbits the sun a little bit less rapidly, and so on for each of the planets. And really, there is a steep dependence here that falls off with the distance, such that the difference between the orbital speed of Uranus and Neptune is not nearly as significant as the orbital speed difference between Earth and Venus, for example, or Earth and Mars, etc. And so this follows a pattern that's expected due to a point mass, where the sun's gravity is what keeps the planets in orbit. And so the farther the planet is from the sun, the weaker the gravity at that point, since the force of gravity scales inversely with the distance squared, and therefore they orbit the sun more slowly. On the other hand, if we look at our galaxy and look at the orbits of stars around the galactic center, it's a totally different pattern. And for the initial rise, this is because we don't have a point mass like our sun at the very center. There is technically the supermassive black hole, but we have a relatively wimpy supermassive black hole at the center of our Milky Way. The mass in stars dominates by a factor of 10,000 um, compared to the mass of the black hole. Well, let me double check those numbers. So the mass of Sagittarius A star we think is around 4 million solar masses. The mass in stars in our Milky Way we think is roughly 100 billion solar masses. We think that there's a total of around 1 trillion stars, but most of them are lighter than our sun, around zero point 0.1 solar masses. Um, yep, so that works out. So it is around a factor of 10,000 difference between our central supermassive black hole and the mass of stars in our galaxy. So, as you're considering concentric radii from the center, we're accruing a lot of stars. And we think that you get to a billion, maybe up to 10 billion solar masses within the first few thousand light years. Now, as far as why the mass continues to stay relatively steady, these oscillations are due to the spiral arms, but why it doesn't just, um, continuously increase and then eventually flatten out and then decay is a big question. And our sun is indicated here, but really the way that we know that the rotation continues to increase despite the number of stars, being truncated within some region, we think that our sun is maybe about 2/3 out, or maybe a half to 2/3 away from the galactic center. So in other words, we'd expect to have really gotten to about 100% of the stars by 60,000 light years. Whereas this is not just constant, but is increasing slightly. Um, and so the reason why we know that, again, there's not many stars to measure there. We're measuring the neutral gas, the hydrogen 1, in the 21 centimeter radio emission line for the most part. There's also like some trace number of stars that have been ejected, just like we have most of the mass is in the sun. We have some mass in planets, and then a pretty, we think, small mass in asteroids and the Kuiper Belt, etc. So there's still some objects in the solar system at larger radii that contribute negligibly, we think negligibly to the mass. Maybe there's some stars that are out here, but mostly we're measuring a neutral gas to make these measurements, at least in the modern day. Um, and so, in other words, we must be missing mass. Otherwise, we'd expect the same sort of rotation curve where as gravity gets weaker, things get slower. So there must be some additional mass that we're missing somehow. Could this just be X-rays? Well, we've measured this not only in our Milky Way, which is a little bit harder to measure the X-rays for the full sky. We've measured it for a number of other spiral galaxies. And these spiral galaxies have different X-ray patterns. It doesn't seem like there's any overlap there. Additionally, if we take a look at the abundance of elements, and specifically deuterium, that's predicted from Big Bang nucleosynthesis, we end up with way more deuterium that is measured compared to what would be predicted to be created in the Big Bang if we had 100% ordinary matter comprising our universe. The reason why this is, the larger the amount of ordinary matter, the easier it is to fuse past deuterium, right? And so you would expect a very small amount of deuterium relative to hydrogen if the universe is totally ordinary matter, whereas as the fraction of ordinary matter decreases, you maintain more deuterium, since less of it's able to fuse into tritium and helium and trace amounts of lithium. And the best match between the deuterium that we measure and this model for how much deuterium should be produced based on the fraction of ordinary matter that comprises the universe matches this 5% mark. So in other words, overwhelmingly, the density of the universe must be comprised of something that is not ordinary matter. And we think that about 5 times as much ordinary matter is in dark matter, and then there's a whole lot of dark energy, as we've talked about before. In addition to considering the deuterium abundance, we also consider the cosmic microwave background. And this gets kind of technical, so we're not going to talk about it in detail in this course. If you take upper level astrophysics courses, you'll go a bit deeper. And again, at the very end of the slides, um, we do talk about this a little bit more, I guess I should say, in the slides, but you'll have an opportunity to go as deep into this as you have time for with our final worksheet for today. So we'll explain this a little bit more later, but these ratio of peaks, really like this first peak to the second and this ratio of the second to the fourth, indicates that most of the matter in the universe is dark, let alone most of the energy density being dark as well. And then what I would call the most smoking gun evidence for for dark matter being dominant in galaxies and structures in our universe is shown by the bullet cluster. So the bullet cluster is actually two different galaxy clusters that have had a collision. We think that this smaller cluster was at the left initially, and then this larger cluster was on the right, and then they passed through each other, where now these two objects seem to be continuing relatively unimpeded in terms of the galaxies, whereas in between them is that X-ray emitting gas. Now remember when I was discussing Fritz Zwicky earlier, I mentioned that in more modern times, we've realized that galaxy clusters are comprised of a factor of 10 more X-ray gas than regular matter, than otherwise regular matter, comprising the stars in the galaxies as well as neutral gas, etc. And so if there was no dark matter, it is a big puzzle how the X-rays would stick towards the center while the galaxies would keep moving unimpeded. If the X-rays were really the dominant form of matter, then the galaxies, which are again quite light, 10 times lighter than the X-rays, you'd expect them to um, still be in the center here, and for these two objects to have maybe coalesced into one cohesive structure. Instead, the fact that the galaxies have continued unimpeded suggests that there is some additional collisionless component that has continued the journey along with the galaxies. And so this is canonically dark matter, although one of the places where this figure shows up most prominently, this Markovich paper, or excuse me, maybe it's not the Markovich paper, but no, it is the Markovich paper, is related to so-called modified gravity theory. So there are some people that are working on non-standard theories to explain away dark matter, but I don't know. I read the paper. I thought it was a little bit far-fetched what they consider. Still worth considering, but it just seems a little contrived to me. Okay, now in terms of what makes up dark matter, we talked previously about the evidence. So just to summarize that again, we have the bullet cluster as evidence, we have the CMB power spectrum as evidence for dark matter, we have the measurements of the amount of deuterium in the universe, and spiral rotation curves of galaxies, and then also galaxy motions in galaxy clusters. So those are our pieces of evidence for dark matter. In terms of what dark matter is made of, we don't know. There are two leading classes of theories, though, that within them have lots of different models. One of those theories are referred to as WIMPs. These are weakly interacting massive particles. So think something like the neutrino, but a whole lot heavier. The other major class are so-called massive accreting compact halo objects, pretty much aka black holes, although technically machos could refer to any more macroscopic massive object. The accreting compact halo part is really saying, okay, that we mean black holes here. But whether these are black holes formed by stars or something more exotic that might have been formed in the early stages of the universe more directly is unknown with some constraints. These could technically, I guess, also be asteroids or comets, which I think is my most fun or preferred mechanism. But for the most part, the constraints on machos are pretty tough, and therefore most scientists favor WIMPs. Although LIGO, the gravitational wave observatory results from 2016, 2017 did lead some people to continue to kind of resturge their interest in machos of there maybe being a certain uh, uh, in other words, black holes of order 10, 20, 30 solar masses being possible and still fitting within weak lensing constraints. But anyway, WIMPs are the preferred mechanism. In terms of how we detect those, maybe we could in space or in particle colliders. There are also these huge cavities. This is Kamiokande in Japan, where they've basically carved out the interior of a mountain and filled it with liquid xenon, or excuse me, this one might be filled with water, maybe deuterium or heavy water, which is mostly deuterium. And then there are all these sensors that are filling this experiment. And the idea is that if any particle interacts, then they'll notice some byproducts. And so far, there have been zero detections, though. The other class, again, is maybe black holes, and LIGO has some interesting results. And we will really have to wait for LISA, the Laser Interferometer Space Antenna, which is being led by the European Space Agency, to really know, arguably, the answer here. And LISA is the number one priority of the European Space Agency. It was confirmed about a year ago, or maybe 6 to 8 months ago at this point. So really exciting. It's still going to take quite a little bit before it flies, but hopefully within the next few years, maybe even by 2030, we'll understand if machos are totally ruled out or if they have maybe they're even more interesting than WIMPs at that point. Now, in terms of how dark matter interfaces with cosmology, the idea is that the formation of galaxies depends crucially on dark matter. And it was the gravity of dark matter that allowed the sufficient gravitational pull and contraction of gas to form stars, is the idea. Initially, halo stars before a significant disk component could form. And the idea for dark matter and galaxies is that since the dark matter is either non-interacting or weakly interacting, they're not able to shock and interact like the regular gas does. And whereas the regular gas forms, a disk, we think, and then maybe with mergers of disks, we form elliptical galaxies, the dark matter always stays in this much more extended and spherical structure, since it can't shed away its angular momentum or its energy. And in terms of the distribution of galaxies, relatively near our Milky Way is the so-called local supercluster. And so we think that our Milky Way is part of a large consortium, you could say, of galaxies. There are a couple of other superclusters that are relatively nearby, and part of this is really a challenge in doing cosmological measurements because rather than everything being totally constant in its motion or, radially away from us, like in Hubble's law, when we consider smaller distances, instead of billions of light years away, millions or hundreds of millions of light years away, we have to take into account that galaxies are actually streaming still. Their dark matter is still pulling them towards the centers of the most massive structures in the universe. So there's still evolution. And in terms of cosmological simulations, the idea is that we, build up these nodes, build up the material with time until we end up with very dense structures ultimately. Okay, and then in terms of like zooming in on these cosmological simulations, again, the idea is that we start out with just some structure. So this is um, really simulating the full universe. And then as we zoom in, it's almost like a fractal pattern. As we zoom in, there's more and more structure until we eventually, you know, get down to the individual galaxies. All right, so in summary for this part, what have we learned? We have seen that the motion of galaxies in galaxy clusters, as well as the gas in galaxies themselves from Vera Rubin, suggest invisible dark matter. There's also evidence regarding the deuterium abundance, which I don't think I've included here, as well as the cosmic microwave background. And we won't talk about closure here, but we will talk slightly more about the power spectrum in the kind of second half of these slides. And then the bullet cluster, I would argue, gives the strongest evidence for dark matter overall. And regarding what dark matter is made of, there are two main leading theories. Dark matter might be made of WIMPs, or these weakly interacting massive particles like massive neutrinos, or dark matter might be made of massive accreting compact halo objects or black holes. And then there are some people that try to come up with alternative gravity theories. Now, in terms of how dark matter is related to the formation of large scale structure, again, dark matter uses gravity to congeal the material around us, and we think that forms progressively more massive nodes and filaments and forms ultimately the large scale structure we observe around us today. Okay, and so now there are two different worksheets for you all to work on. There is a rotation and dark matter worksheet, as well as a dark matter bullet cluster worksheet. And so the idea is to make sure that you are really absorbing this material from yourself rather than hopefully not just listening in a bit of a stupor. So go ahead and pause the video and try completing those worksheets. I would suggest spending anywhere from 20 to 40 minutes per worksheet, although maybe you will be quite a bit quicker. Okay, so pause the video. Okay, unpause. Hopefully you completed those two worksheets. And the next part of this lecture is getting into the CMB power spectrum. And I apologize that this video is coming out so late. I really had some trouble coming up with appropriate slides, and in the end, I decided to dip my toes into some AI generated slides. Towards the beginning of the semester, some of you, I think a minority, but most of you just did not respond. But some of you said that you kind of liked the formatting, at the very least, of the AI slides that I've done previously. I still don't really love it, but I use that to assist with the generation of the slides moving forward. As you'll kind of obviously tell, they were produced with Notebook LM, which is through Google, so basically Gemini. And for our goals of learning for this part, we'll be digging into basically why there should be temperature variations in the CMB at all, and why we can kind of immediately know that there had to be temperature variations. Otherwise, there's a huge problem if the CMB was perfectly uniform. For attention check 7, we'll talk about why Kobe observed the CMB at different frequencies to really prove this was the case, or at least give high evidence that there are temperature variations. And then for attention check 8, we'll discuss the space-based and ground-based missions that really followed up on Kobe. All right, and so again, really kind of pretty slides generated by Notebook LM. So in terms of cosmic microwave background, so again, the idea is that we have the Big Bang, and then with time, we have the evolution of the universe, as we've been learning about. Next week, we'll talk a little bit about inflation. And in terms of the afterglow from the Big Bang, again, this has to do with the uh, material in the universe switching from being ionized and so-called recombining to form atoms. And the expectation would be a perfect black body. So we expect a peak at around 2.7 Kelvin, and then for there to be a very regular decay, a exponential decay on the bluer wavelengths, or the hotter parts of the spectrum, and then a Rayleigh Jean's tail, which varies with the wavelength of to the minus 2 power on the opposite side. And in terms of why the CMB can't just be a perfect uniform uh, black body, but why there have to be temperature variations, is that we would not exist otherwise, because we need there to be slight variations in order for dark matter to tug, or gravity in general to tug material together to form structures in the universe. Um, so, in terms of uniformity, it's true that we think that in cosmology, the largest scale of the universe is homogeneous, but we do still need, on small scales, some fluctuations, not just in temperature, but also, more importantly, although relatedly, in density, in order to form, again, galaxies and ultimately people. So this was not easy to identify, though, in cosmic microwave background measurements. For one thing, there is a so-called cosmic dipole that people measured at around 3 millikelvin, so about 1,000 times smaller in signal compared to just the overall cosmic microwave background. And the reason for this dipole is due to, well, at the very least, Earth's motion around the solar system. So Earth is sometimes, moving towards the sun, sometimes moving away from the sun in its orbit, or maybe, excuse me, in terms of the kind of relation to the CMB, it looks like that way. It looks that way due to the rotations. There's a blue shifted component and a red shifted component, where the universe looks slightly hotter in the direction that the Earth is moving kind of towards the CMB, and then a redshifted component for where the Earth appears to be moving away from the CMB. So we have this dipole component, which also shows up in cosmic ray measurements, kind of interestingly. And in addition to the dipole from Earth's motion around the sun, there's also the solar system's motion around the galaxy, which also forms a dipole, although the much stronger dipole is Earth's motion itself. And in addition to the Earth moving around the sun and the sun moving around the galaxy, our own galaxy is also moving, and not just our galaxy, but the so-called local group of galaxies is also moving around 600 kilometers per second. So it's not just that we need to subtract off Earth's motion, or just that we need to subtract off the sun's motion around the galaxy, or the Milky Way's motion with respect to Andromeda, but we also have to consider the local group. And so this makes it very, very challenging to notice the expected variations that were left over from the Big Bang, because this dipole component is, again, around a millikelvin, or 3 millikelvin. So in other words, it's 1 part in 1,000 compared to the signal. Whereas our expectation, once we've removed all these sources of noise of local motions for the original temperature variations, as predicted by George Smoot, was about 1 part in 10 to the 5. Or in other words, about 10, or around 20 to 30 micro Kelvin, not milli, but 1,000 times smaller for the micro part, and then 10, so it's more of, again, 1 part in 10 to the 5. And so that is a huge, huge issue, because in the medical field, for example, people tried to detect signals of 1 part in 10 to the 5 by subtracting off backgrounds that were 1 part in 10 to the 3. And what they found in the medical world is so-called ghost signals. So in other words, just artifacts of the background subtraction process that are not actually physical. And so people thought that when Smoot was doing this, that these were also just kind of ghost signatures. Now, in terms of making sure that everything gets subtracted, and to make sure that there were not ghost signatures, this is why COBE used multiple frequency bands. So COBE measured the cosmic microwave background not at one single frequency like Penzias and Wilson did, but considered 3 different frequency bands of around 30 gigahertz, 50-ish gigahertz, and 90 gigahertz. For one thing, that also allows us to check the blackbody curve of the CMB. So if we're considering different frequencies, we can measure 3 different points. That's not really, very well sampling the curve, but we can still take a look and make models. So it's kind of a first look at the cosmic microwave backgrounds fit to a black body. And then this also means that, if there were ghost patterns, we'd expect those during the subtraction process to show up in one of the bands, but it'd be very strange for them to show up in all of them. In particular, one element that I didn't quite discuss earlier, this galactic synchrotron and dust emission, um, these are less about motions that we have to subtract off, like the Doppler dipole, but these are additional signatures. So just like on Earth, at first Penzias and Wilson were concerned that maybe the Hornbill horn antenna was picking up its own temperature or its own like radio signal from its temperature. Galactic dust, unfortunately, is also right at this um, microwave emitting frequency where we have to remove the dust as well as the so-called synchrotron emission. This is due to ionized electrons for the most part. And so we have to remove these signals in order to see the early universe. The good news is that the galactic dust and synchrotron can be kind of isolated to a certain frequency range, and the Doppler dipole also varies differently for the different frequencies. So we can be really confident now. And as a result of this work, John Mather and George Smoot were awarded the 2006 Nobel Prize. So this was, not immediately, but still 14 years after the measurement by Kobe leading to the Nobel Prize is still pretty quick. And again, these temperature variations are really the seeds or these overdensities that lead to the formation of large-scale structure observed today. Now, Kobe is still limited, though. You can see that this image is quite grainy. And in terms of really understanding like the role of dark matter or dark energy, which was not really known. Dark energy wasn't really known in 1992, but dark matter, there's already pretty solid evidence. In order to assess those things, we need higher angular resolution to really be able to distinguish between the hot spots and the dark and the cold spots. And with time, we have launched additional missions, and we have found much more clearly the expected around 18 microkelvin variations forming large scale structures. And in terms of like why it is that there are temperature variations, when we have galaxy clusters, they form, or galaxies or any massive object, we think that for general relativity, that means that that massive object is warping spacetime. And the more mass, the more spacetime gets warped. So if we are dealing with big galaxy clusters now, it takes a significant amount of energy for the light to leave the gravitational potential well, and that causes a gravitational redshifting of the light. And we've observed this in our own solar system as well, that there is a gravitational redshifting of light even within Earth's gravitational potential well, which is, puny. And so this causes certain regions to look colder due to the light being redshifted. And then there are certain regions where photons lose less energy, and thereby they appear kind of hotter. But in all cases, it's simply that the photons lose some energy, not that the photons are gaining some energy. You need a negative curvature, in other words, some not just antimatter, but some really exotic matter to do that. It'd have to be a negative matter. Okay, and then in terms of the formation of the cosmic microwave background's angular power spectrum, the idea is that there are so-called acoustic waves. So in the same way that you are able to hear me due to sound waves traveling through the air, which are causing compressions and rarefactions of the air density. The same thing happens in the universe where there's gravitational attraction, but as more material gets compressed, the energy from the photons, the energy from that gas, is also increasing, and that means that there's a radiation pressure acting kind of on the in the opposite direction, which is trying to smooth things back out again. And what happens ultimately is that there's, just like for Cepheid stars, there's kind of a overcorrection. There are some waves that are propagating because there's slight over attraction and slight over expansion. And so these series of uh, you know, temperature variations in the CMB, hot spots, cold spots, hot spots, cold spots. These are really alternating due to this so-called tug of war. And in terms of the angular power spectrum, you might have noticed that there's some regions where there are really big hot spots and really big cold spots. And then there's some spots that have really smaller hot spots, smaller cold spots. That's what's being shown in the angular power spectrum. So if we consider the largest scales, which is what Kobe was measuring, again, Kobe was much more smoother, right? So we're only seeing the larger scales for Kobe, about 7 degrees. Whereas now we're able to look with sub-arcsecond resolution. Um, and so over time, we're able to notice more and more elements. Let's just kind of skip ahead here, um, thinking about WMAP and Planck next. So again, we saw this for Kobe. For WMAP, this went from 7 degrees in the angular resolution down to 15 arc minutes. And maybe I was a bit exaggerating when I said arc seconds. For Planck, um, we've significantly increased the resolution still, or I believe it's sub arc minutes at this point, and in fact arc seconds. But really, WMAP was useful in proving to skeptics that no, it wasn't just one satellite that measured these temperature variations. And WMAP had a good enough resolution where we could measure acoustic oscillations and was able to establish the contributions to dark energy, dark matter, kind of the cosmic pie chart that we use today in our experiments and simulations. And then Planck was able to get these cosmological parameters like the amount of dark energy, the amount of dark matter, etc., down to less than 1% accuracy. So we've seen this tug of war before. In terms of how that relates to the power spectrum, the idea is that depending upon, there's not just one of these potential wells, but there's many, many, many galaxy clusters that form in the universe. And within the like size of this well, you have different frequencies that or standing wave patterns that are possible. So in terms of measuring like the first peak of the CMB power spectrum, this is largely responsible for like how flat versus curved the universe is. For the second peak, this allows us to better understand how much ordinary matter is going in related to these oscillations or these waves. And for the third peak, the amount of dark matter influences at smaller scales how much matter is able to be pulled in. And so this is true all the way down. And by measuring not just the first peak, or first two peaks, but by measuring the first three, we're able to look at the ratio of those acoustic waves and find the amount of dark matter that exists. And so with time, we've been able to go from, just measuring the large scale structure of the universe through to WMAP and Planck, really getting very, very high accuracy results where, again, for Planck, I believe this is sub-arcsecond resolution now. So this multipole moment, we were just looking at the first three peaks. This multipole moment, in other words, we're looking at 2,000 peaks or 2,500 peaks. Um, and let's go ahead and skip this. So in other words, just Planck is much, much more accurate than WMAP or COBE. Now, last kind of important part here is in addition to WMAP and Planck being successors space-based, we unfortunately have not had another space-based CMB experiment since Planck. What's been leading the charge since then have been a series of ground-based experiments, namely the Atacama Cosmology Telescope, the South Pole Telescope, and the BICEP or mission or BICEP Keck array. And for these different telescopes, they're really working in some ways together, in some ways separately, to understand better the cosmic microwave background, and therefore, okay, although we think from WMAP and Planck that the universe is extraordinarily flat, is it perfectly flat? Is there a slight amount of curvature? And really, the most important thing today that people are looking for is related to E modes and B modes. The E modes have to do with so-called reionization and better constraining galaxy formation physics, whereas B modes have to do with the very early epoch of inflation, which and we'll more of talk about next time, and therefore are able to test this kind of extension, or at this point, fairly standard extension to the Big Bang Theory. And it's really, I would say, pretty incredible um, that we've been able to go from simply measuring the existence of the CMB with Penzias and Wilson in the 1960s to within 50 years later with WMAP and Planck really having, or at this point, kind of 60 years later with South Pole Telescope and BICEP Keck, that we really have a high precision view of the universe. We know what the universe is made of to sub% accuracy at this point. And again, you all have now an opportunity to dive into the power spectrum and to better understand for yourself at a much more tactile level how this works. And BAO stands for baryon acoustic oscillations that are really kind of the key process that drives the shape of the power spectrum, at least when considering ordinary matter and dark matter for the second and third peaks. So this is the end of the lecture. It depends how long it took you for the first two worksheets, but I would suggest spending a significant amount of time on this final worksheet, and you'll get to explore, really, I think, in quite a fun way, a series of animations and additional explanation by one of the leading cosmologists in the field who's located at the University of Chicago now. All right, so have a good rest of your day. Until next time, bye bye.